Hello my friends and welcome back to the You Can Do TV channel. Copper Mountain Mine, an open pit operation near Princeton, BC, specializes in extracting copper, gold, and silver. The process begins with large-scale mining, using a fleet of advanced equipment, including hydraulic shovels, haul trucks, and rotary drills. Approximately 175,000 tons of material are moved daily, with 35,000 tons of ore delivered to the primary crusher. The ore is reduced to 6-inch fragments by a 60-inch primary crusher and transported via a kilometer-long conveyor to a coarse ore stockpile. From there, it enters the concentrator, starting with a 34-foot sag mill, which grinds the ore using steel balls. Finer particles are screened and fed into ball mills for additional refinement. Coarser material is recycled through a pebble crusher before rejoining the milling process. The ground ore undergoes flotation, where copper minerals adhere to air bubbles and rise for collection. Initial concentrate, containing 5% copper, passes through regrinding and cleaner flotation to achieve a 25% copper concentrate. The concentrate is thickened, filtered to reduce moisture, and trucked to Vancouver for export and smelting. The copper mining and smelter refinery plant bore has undergone significant advancements through brownfield investment projects, with microcontrol leading several automation initiatives. Key upgrades include the control systems for raw material processing, transportation, the conversion plant, refinery, and sulfuric acid plant. The slag grinding process involves a 150 kilowatts crusher, transporting material to vibration sieves and a secondary crusher, achieving a capacity of 150 th. Post-grinding, material is directed to two mills, one of which features a 5.25 kilovolts, 300 kilowatts motor. Advanced PLC and HMI software manage LV panels, hydrocyclone pumps, and compressors. The smelter converts concentrate into anode copper, with liquid copper refined to 98% Cu before precise weighing and casting into anode plates. Automated systems streamline transport and production, enhancing efficiency. India's pure copper and copper-based products industry is a vital component of the country's industrial framework, driven by demand from sectors such as construction, power, and telecommunications. The annual production capacity of refined copper in India is around 1 million metric tons, with the country playing a significant role in the global copper market. India produces a wide range of copper-based products, including rods, wires, sheets, pipes, and alloys, catering to both domestic and international markets. Exports of copper and copper-based products have grown steadily, reaching approximately $1.8 billion in 2022, with major export destinations including China, South Korea, and the Middle East. The copper industry is bolstered by increasing investments in renewable energy, electric vehicles, and infrastructure development, all of which require extensive use of copper for wiring, motors, and structural components. The demand for copper in India is projected to grow at a compound annual growth rate of 5 to 6% over the next decade. Challenges like fluctuating global copper prices, reliance on imported raw materials, and environmental regulations persist, but the industry remains a cornerstone for India's industrial growth and economic development. The synchronous compensator production industry in Brazil plays a crucial role in stabilizing the country's electrical grid, supporting efficient power transmission, and enhancing voltage regulation. Synchronous compensators, or synchronous condensers, are used to provide reactive power support, helping to maintain voltage stability and grid reliability, especially in regions with fluctuating demand or high levels of renewable energy integration. One notable achievement in the Brazilian synchronous compensator industry is the production of the largest compensator ever made in the country. This colossal equipment comprises two identical units, each weighing an impressive 310 tons. These massive machines stand 7 meters high and extend to a length of 11 meters, making them among the largest of their kind globally. Brazil's energy grid is increasingly dependent on renewable energy sources like wind and solar, which can be intermittent. The demand for synchronous compensators has risen as utilities seek to ensure grid stability. As of 2023, Brazil's renewable energy capacity stood at over 150 gigawatts, with wind power alone contributing approximately 22.4 gigawatts. This growth in renewable energy has driven investments in reactive power technologies. Currently, Brazil has a limited number of manufacturers involved in the production and supply of synchronous compensators. Some major players in the market include global companies with local operations, such as AB and Siemens, who have been involved in projects to provide grid stability solutions. However, domestic production capabilities have been growing in recent years, driven by the need for localized manufacturing due to the increasing demand for grid modernization. The Brazilian market for electrical equipment, including synchronous compensators, is valued at approximately $7 billion in 2024, with a compound annual growth rate, CAGR, of around 4.5%. The government's ongoing investment in infrastructure, such as the expansion of transmission lines and the implementation of smart grid technologies, is expected to further drive demand for synchronous compensators. The production process begins with heavy shearing of raw materials to prepare them for precise machining. Leaf spring manufacturing is a highly specialized process carried out in two advanced facilities located in Jamshedpur, India. These plants collectively produce 12,000 metric tons of parabolic leaf springs and 18,000 metric tons of multi-leaf springs annually. This is followed by CNC drilling to create accurate hole placements and hot punching for forming apertures. These operations ensure the raw material's integrity and structural stability, setting the foundation for subsequent manufacturing stages. Parabolic leaf springs undergo an automated rolling process designed to maintain high accuracy and efficiency. The eye rolling and taper rolling stages shape the spring ends and optimize the material thickness to handle load distribution efficiently. Equipped with extensive R&D and testing capabilities, including cutting-edge chemical and metallurgical labs, computerized profiling machines, and German fatigue life cycle test rigs, these facilities ensure exceptional product quality. Their in-house design capabilities allow them to customize multi-leaf, parabolic leaf springs, and air links based on customer specifications. These steps are performed with high precision to ensure the structural integrity and performance of the springs. The use of a gas-fired end heating furnace minimizes decarburization, ensuring a high-quality surface finish. A CNC servo-controlled rolling machine guarantees precision in shaping the parabolic profile, while a high-pressure descaler removes surface scale, maintaining control over the final profile. The heat treatment process is a critical stage that employs advanced robotics for consistent results. Robotic systems ensure uniform timing during the transfer of leaves from the austenizing furnace to the cambering process. The gas-fired furnaces used in this stage optimize energy consumption and ensure uniform heat distribution, enhancing the microstructure and surface quality of the springs. An online straightening machine is used for removing lateral bends from springs longer than 1,000 millimeters. The quenching process, featuring a swinging mechanism for rapid cooling, combined with extended cambering under clamped conditions, results in superior mechanical properties and camber stability. To improve durability and fatigue resistance, the springs undergo stress shot peening. This involves dual-pass machines equipped with turbines and varying shot sizes to ensure complete coverage. The process enhances compressive residual stress on the surface, significantly improving the spring's fatigue life. Automated systems, including sieve shakers, maintain shot quality, and presses are used for stress peening parabolic leaves. A multi-station press reduces the need for multiple heating cycles, preserving material properties and streamlining operations. Profile checking gauges are employed to verify the accuracy of the parabolic profile before moving to the next phase. The springs are then coated in an automatic painting line to provide superior surface protection and finish. The electrostatic bell system enhances production efficiency, while a dust-free environment ensures excellent paint adhesion and a flawless surface. An overhead conveyor system facilitates seamless handling, ensuring high throughput. In the final stages, the springs are assembled and scragged using a conveyorized system that minimizes handling damage and enhances material quality. Hydraulic clamping presses eliminate the need for hammering, preserving the surface integrity of the components. Online scragging machines operate in both load and deflection modes, ensuring dimensional accuracy and reliability. The machines at Mechanica Zella operate with precision and versatility, enabling the company to handle a wide range of machining tasks. The CNC-controlled boring machine plays a central role, capable of performing internal precision machining with high accuracy. This machine is designed to bore pieces with dimensions up to 3,500 by 1,200 by 2,000 millimeters in height and features a CNC boring and facing head that can handle diameters up to 1,000 millimeters. Lathes are equipped for both external machining and deep internal boring. They can handle pieces with diameters ranging from 250 millimeters to 1,250 millimeters, reaching depths of up to 2,200 millimeters. These lathes are capable of turning pieces, including shafts, with diameters up to 1,450 millimeters and lengths of up to 6 meters. Advanced CAD/CAM 3D systems control the machining phases, ensuring that each operation meets the required specifications. The machines are programmed to execute various work cycles with high precision, and quality checks, such as ultrasonic and magnetic particle tests, are conducted to guarantee the integrity and reliability of the final product. India's fastener production industry is a critical component of its manufacturing sector, catering to automotive, construction, aerospace, and general engineering needs. Valued at approximately 34,000 crore rupees, 4 billion United States dollars, as of 2023, the industry is projected to grow at a CAGR of 7 to 8%, driven by infrastructure projects and rising automobile production. India produces both standard fasteners, like nuts, bolts, and washers, and customized fasteners for high-performance applications. The country has around 900 fastener manufacturing units, concentrated in hubs like Ludhiana, Pune, Chennai, and Bangalore. The organized sector accounts for 60% of production, while the unorganized sector caters to domestic low-cost demands. The industry exported fasteners worth 10,000 crore rupees, $1.2 billion United States dollars, in 2023, with major markets including the US, Germany, and the Middle East. Adoption of advanced manufacturing technologies, such as CNC machining and surface treatment processes, is bolstering quality and competitiveness in the global market. Key processes in lumber production. Harvesting and log transport. The process begins with timber harvesting, primarily conducted through selective logging or clear-cutting methods. Sustainable forestry practices are widely employed, with many companies adhering to certifications such as the Sustainable Forestry Initiative, SFI, and Forest Stewardship Council, FSC. Logs are then transported to sawmills using trucks or rail. Debarking and sorting. At the sawmill, logs are debarked to remove the outer bark layer. This step minimizes equipment wear and improves processing efficiency. Logs are sorted based on species, size, and quality to optimize yield and meet customer specifications. Primary breakdown. Logs are fed into large saws or band mills, where they are cut into rough shapes such as cants or planks. Advanced sawmills use computerized optimization systems, employing 3D scanners and laser technology to maximize wood recovery and reduce waste. Secondary breakdown and resawing. Rough lumber undergoes further processing to achieve specific dimensions. Resawing involves cutting cants into boards of varying widths and thicknesses. Mills often produce standard sizes for construction purposes, including 2x4s and 2x6s. Sustainability and challenges. The U.S. lumber industry is committed to sustainable forest management, with annual tree growth consistently outpacing harvest levels. However, the sector faces challenges like fluctuating demand, labor shortages, and supply chain disruptions. Emerging technologies like AI-driven sawmills and carbon-neutral operations promise to enhance efficiency and sustainability in the future. Overview of lumber production. The U.S. is the largest producer of softwood lumber globally, with significant contributions from regions like the Pacific Northwest and the South. These regions offer vast forest resources, including species like Douglas fir, southern yellow pine, and spruce. The South accounts for nearly 60% of U.S. softwood lumber production, driven by faster tree growth rates due to its favorable climate. Drying. Lumber is dried to reduce moisture content and improve strength, stability, and resistance to decay. This step typically involves kilns, where controlled heat and airflow reduce moisture to desired levels, usually 8 to 19% depending on end-use requirements. Planing and grading. Once dried, the lumber passes through planers to achieve smooth surfaces and consistent dimensions. Grading systems evaluate the quality of each piece, categorizing it as structural, appearance grade, or industrial lumber. The lumber production industry in the United States is a vital part of the nation's economy and manufacturing infrastructure, contributing significantly to construction, furniture, and paper industries. In 2023, the U.S. lumber market reached an estimated value of $130 billion, with sawmills producing approximately 45 billion board feet of lumber annually. The industry directly employs over 500,000 people, supporting thousands more indirectly through logistics, equipment manufacturing, and downstream operations. Packaging and shipping finished lumber is bundled, wrapped, and shipped to wholesalers, retailers, or directly to customers. The production process of wooden toys begins with the purchase of raw wood materials, typically choosing hardwoods for durability. The wood is then pressure planed to achieve a uniform thickness, followed by polishing for a smooth surface. Afterward, it is cut into specific shapes, and detailed features are created through drilling, milling, and tenoning. The edges and surfaces are further refined by sanding to remove any rough spots. Next, the wood undergoes humidity inspection to ensure moisture content is within acceptable limits, as excessive moisture can cause warping. Once shaped, the parts undergo inspection for precision before being glued or assembled using adhesive. Another round of inspection ensures a proper fit. Next, the toy parts are sprayed or painted using a roller for even application, followed by a color test to check consistency. The painted parts are rechecked during inspection, and then the final assembly is completed. A comprehensive final inspection ensures quality, after which the toys are packed for shipping. The electric motor wrecker is designed to disassemble electric motors and separate copper windings from silicon steel. It handles motors with internal diameters ranging from 0.100 to 0.500 millimeters. The machine operates at high speed, enabling efficient separation. Once the motor is placed in the machine, its cutting and pulling mechanisms extract the copper windings while simultaneously processing the silicon steel core. This streamlined process simplifies recycling, improves efficiency, and saves significant time. The Bano Premac 22 Hydro single-shaft shredder processes copper transformer coils efficiently, combining versatility and precision. It features a hydraulic or mechanical drive system and a sliding hopper bottom for safer, quicker maintenance. Equipped with interchangeable and reversible blades and counterblades, the machine minimizes downtime and replacement costs. The shredder incorporates a pusher that ensures constant, self-regulated rotor feeding, significantly enhancing throughput. An interchangeable screen enables precise output size control during shredding, eliminating the need for additional processing steps. Its structure, built with a robust 100 mm frame, ensures durability. Additionally, the safety clutch, in the mechanical version, and active protection system for bearings improve operational safety. The production of brass rods involves a sequence of precise manufacturing steps using specialized machinery and equipment to ensure high-quality output. The process begins with melting brass scrap, typically composed of copper and zinc alloys, in a brass melting holding furnace. The furnace provides controlled heating to liquefy the material, ensuring a homogeneous composition. The molten brass is then directed to a special brass rod casting machine, where it undergoes controlled cooling and solidification. The formed rods are subsequently cut to the required lengths using a brass bar cutting machine. A cooling crystallizer combined with forming dies shapes the brass into rod form as it solidifies. This step ensures the desired diameter and smooth surface finish. Throughout the process, smoke and dust collectors maintain a clean and environmentally compliant workspace by capturing emissions and particles. The 25 meganewtons direct-indirect tube extrusion line at Sarbak Metal Factory in Çerkezköy, Turkey, represents a fully automated and integrated production system designed for high performance and precision across a diverse range of products. The process begins with automatic billet loading, accommodating billet lengths from 300 to 800 mm and diameters up to 240 mm. Billets are precisely positioned for the front loader operation. The system supports both direct and indirect extrusion methods, using a multi-axis manipulator for handling loose dummy blocks and scavenger blocks. The system ensures accurate management of profile IDs, set IDs, and alloy specifications, controlled through a centralized panel with a Pico's visual display system for real-time monitoring. Extrusion speeds are controlled for consistent performance, with data such as actual extrusion speed and target speeds displayed for operator reference. After extrusion, products are cooled on a walking beam cross conveyor integrated with a cooling table. A high-performance finishing saw with chip extraction and cutting diameter adjustment ensures clean, precise cuts. The finished products are transferred via cross conveyor to moving deposit tables. This automated handling system guarantees optimal reproducibility and product quality. The line is capable of processing hollows with diameters up to 150 mm and sections up to 180 mm in width. Additional features include an indirect extrusion capability and a wire rod coiler, supplied externally. The fully automated cleaning process further enhances production efficiency. The entire system, designed and supplied by the SMS Group, delivers a coherent and customized technological solution tailored to meet stringent product quality and operational efficiency requirements. The machine operates by first shredding materials into smaller pieces for easy handling. Its robust design ensures high efficiency in breaking down complex structures, including home AC radiators, industrial radiators, waste car bodies, excluding specific components like engines, reducers, and tires, tinplate, and household appliances, excluding motors, compressors, and shafts. It also processes items like bicycles, truck fences, empty cans, after cleaning and paint removal, other scrap steel, and steel plates or sections with thicknesses under 4 mm. With its high-power motor and durable construction, the shredder effectively reduces materials into manageable sizes while enabling the separation and recovery of valuable metals like copper and aluminum. This 315 kilowatts vertical shredder line, designed for a customer in Qatar, is engineered to handle a range of applications with precision. It combines copper-aluminum separation capabilities with adaptability for processing other materials, making it a compound production line suitable for diverse recycling needs. Alunorf, the world's largest aluminum smelter and rolling mill, is a pivotal player in aluminum recycling. The facility operates a self-contained cycle, ensuring no material is wasted. Annually, its 3 state-of-the-art recycling furnaces melt 150,000 tons of aluminum scrap, transforming it into new ingots. This process supports sustainable production for industries like automotive, packaging, and construction. By utilizing recycled aluminum instead of primary aluminum, Alunorf achieves energy savings of up to 95%, reducing CO2 emissions by 1.2 million tons each year. Advanced processes like sawing, milling, hot rolling, and cold rolling ensure high-quality products while minimizing resource use, setting a benchmark for sustainability and innovation in the industry. The process begins with a mixing and foaming unit that prepares the concrete mix, which is then poured into molds. A ferry vehicle transfers molds to a steel wire device, where they are positioned for curing. The curing process involves the blocks and molds being maintained in a controlled environment to ensure proper hardening. Once cured, an automatic demolding machine with dual workstations removes the blocks from the molds. The blocks are then handled by a forklift for cutting into smaller sizes. A top waste cutting machine trims any excess material. The cutting line includes a dual disc saw for large cuts, a 90-degree corner conveyor, a turning machine, and a small cutting machine for final shaping. The polystyrene concrete blocks machine is designed to produce energy-efficient, self-insulated building blocks. The finished blocks are grouped and stacked using a stacking machine, ready for transport and use in construction projects. The ceramic cookware industry in China has experienced significant growth, driven by increasing domestic demand and global exports. In 2023, the market size of China's ceramic cookware was valued at approximately $10 billion, with a projected annual growth rate of 8% over the next 5 years. The country is the world's largest producer and exporter of ceramic cookware, accounting for nearly 50% of global exports. Major export destinations include the United States, Japan, and Europe. China's ceramic cookware is popular for its eco-friendly and health-conscious appeal, featuring products like non-stick pots, pans, and bakeware. The brick production process here is a fully automated and streamlined operation, ensuring high-quality output. It begins with the mass preparation stage, where clay are crushed, refined, and mixed to create a consistent blend. The introduction of the new monoblock extruder marks a significant advancement, providing precise shaping of bricks with improved uniformity and efficiency. Following extrusion, the bricks enter the drying phase, where controlled environments gradually remove moisture, preventing cracks and deformation. The automated process further optimizes production, reducing manual intervention and enhancing overall efficiency. The dried bricks are then moved to the firing stage in advanced kilns, where high temperatures solidify the material, giving the bricks their strength and durability. Stringent quality control measures are employed throughout the process to ensure each brick meets rigorous standards. To improve logistics, the factory utilizes a new automatic palletizing system, streamlining packaging and handling. Finally, the finished bricks are prepared for expedition, ensuring efficient delivery to customers. The process begins with clay preparation, where raw clay is crushed, mixed, and shaped into bricks using automatic molding machines. These bricks can be solid or hollow, depending on the desired specifications. Once formed, the bricks are transported to the drying kiln, where moisture is removed under controlled conditions to prevent cracking or warping. After drying, the bricks are transferred to the mobile rotary burning kiln. This innovative kiln design features a rotating drum that ensures uniform exposure of the bricks to heat. The rotation allows consistent firing, producing high-quality bricks with even hardness and color. Automated control systems manage temperature, air circulation, and firing time to optimize efficiency. The mobile rotary bricks burning kiln is a key component of fully automated clay brick production lines, capable of producing 5,000 to 30,000 bricks per hour. This system ensures efficient and continuous firing of bricks with high uniformity and energy efficiency. Finally, the fired bricks are unloaded and stacked automatically, ready for packaging or direct distribution. This integrated, automated process minimizes labor requirements while maximizing production output and quality. It begins with raw material preparation, where a balanced mixture of clay and water is crafted to achieve the perfect consistency. For round shapes, the material is cut by hand to match the product size. While liquid clay is manually portioned for other forms during the pouring stage. In molding, the clay assumes its initial shape, followed by unmolding, where the product emerges and undergoes hand corrections. The production process of Staub ceramic cookware embodies precision and craftsmanship at every stage. The cookware is then baked in a kiln, where intense heat transforms it, and its colors come to life. Trimming ensures each piece is refined to perfection. While detailing by skilled artisans imbues the cookware with its unique character. Showcasing Staub's commitment to fine craftsmanship. The products are then air-dried to enhance their strength, preparing them for the next stages. Glazing involves meticulous hand application of vibrant colors, a process that demands exceptional precision. Once baked, the cookware undergoes polishing, ensuring a smooth finish for optimal performance. Afterward, the products are stored for thorough quality inspection. The final step is packaging, where the cookware is cleaned, carefully packed, and made ready to deliver the joy of exceptional cooking to kitchens worldwide. The brass fittings production industry plays a vital role in plumbing, automotive, electrical, and industrial applications due to brass's durability, corrosion resistance, and machinability. Globally, the brass fittings market was valued at approximately $2.5 billion in 2023 and is projected to grow at a CAGR of 4.8% from 2024 to 2030. Key producers are concentrated in countries like India, China, and the United States, with India alone accounting for over 15% of global exports, producing around 85,000 tons annually. Brass fittings are manufactured using processes such as casting, extrusion, machining, and forging, with specific alloys like C36000 and C38500 commonly used. The industry emphasizes precision, producing fittings with tolerances as tight as plus or minus 0.01 mm to meet stringent specifications. Automated CNC machines dominate the production landscape, improving efficiency and reducing waste by 15 to 20% compared to traditional methods. Demand is driven by sectors such as residential construction and water supply systems, with rising environmental concerns spurring innovations in lead-free brass fittings. WEG manufactures turbines and generators for hydroelectric plants with a focus on efficiency, precision, and sustainability. The production process begins with advanced design, utilizing state-of-the-art software to create customized and robust solutions tailored to specific project requirements. The manufacturing phase employs cutting-edge equipment and technologies, enabling high precision and consistent quality. Each component undergoes rigorous process control and quality assurance measures to ensure optimal performance and reliability. Assembly is carried out by an experienced in-house team, ensuring seamless integration of components into compact, efficient systems. This approach minimizes maintenance needs and enhances operational longevity. WEG's commitment to innovation drives constant advancements in design and manufacturing techniques. The result is a range of hydropower solutions that deliver high performance, reduced environmental impact, and maximum trustworthiness, aligning with sustainability goals while meeting diverse energy needs. A screw flight forming machine can produce helical flights with specifications D600, outer diameter, D219, inner diameter, T380, pitch, and S20, thickness, from 09 G2S steel without heating. The process relies entirely on hydraulic force for precision. The steel is pre-cut to size and clamped securely in the machine. High-pressure hydraulic cylinders then form the steel into the desired helical shape. This cold-forming method ensures consistent dimensions and minimizes material distortion, even when working with a maximum thickness of 20 millimeters. The production of screw piles involves several key steps, starting from cutting blade components to the final painting of the assembled pile. Cutting the blades. The process begins with a CNC plasma cutting machine, designed for precision cutting of metal sheets. Bending the blades. Once cut, the flat blade pieces are bent using a press to achieve the desired curvature. This step ensures that the blades can effectively displace soil during installation, providing stability to the pile. Cone formation. The pile tip or cone is formed by cutting triangular pieces, often referred to as roses, from steel sheets. Welding blades to the cone. After forming the cone, the blades are welded to it. This requires precision to align the blade angle correctly, ensuring optimal performance during installation. These are bent into a cone shape and welded along the seams. This conical tip allows for easy penetration into the ground. Typically, a 1.5 x 3 meter working table and a plasma source, such as Hypertherm, are used. The machine cuts blades from 5 mm thick steel sheets, with some manufacturers utilizing galvanized templates for accuracy. This process ensures durability and functionality in construction applications. Surface treatment and painting. The final step involves cleaning the welded assembly and applying a protective paint coating. The coating prevents corrosion and extends the lifespan of the screw pile. Stainless steel coils. The production of stainless steel coils begins with melting and casting. High-quality raw materials, including chromium, nickel, and iron, are melted in an electric arc furnace. The molten metal is then cast into slabs, which undergo hot rolling to reduce thickness and increase length. The slabs are rolled at high temperatures to produce hot-rolled coils. Stainless steel welded pipes and tubes. The production of stainless steel welded pipes and tubes begins with slit coils, cut to the desired width. The coils are fed into a tube mill where they are formed into tubular shapes. The edges are joined using high-frequency welding, HFW, or laser welding to create a strong and seamless-looking weld. Post-welding, the pipes and tubes undergo seam planishing to smooth the weld bead and enhance aesthetic appeal. Heat treatment processes such as annealing improve the material's mechanical properties and corrosion resistance. Straightening and calibrating ensure the dimensional accuracy of the tubes. Surface finishing, including pickling and passivation, is applied to remove impurities and enhance corrosion resistance. Final testing and inspection, including ultrasonic, eddy current, and pressure tests, verify the structural integrity and compliance with standards. Stainless steel butt weld fittings. The raw material is cut and shaped into the desired configuration, such as elbows, T's, or reducers, using processes like forging or machining. For seamless fittings, the material is heated and molded, while for welded fittings, pre-formed sheets or pipes are welded together. Heat treatment, including annealing, ensures mechanical strength and corrosion resistance. After forming, the fittings undergo machining and grinding for precise dimensions and surface smoothness. Rigorous quality control tests, including hydrostatic, dimensional, and radiographic testing, ensure compliance with international standards like ASTM. For cold-rolled coils, the hot-rolled coils are pickled to remove surface impurities and then passed through a cold rolling mill for further thickness reduction. The coils are subsequently annealed to enhance ductility and stress relief, followed by precision surface finishing processes like grinding, polishing, or coating. The production of stainless steel butt-weld fittings involves multiple precision steps to achieve accurate dimensions and flawless finishes. Raw material selection is critical, typically using stainless steel sheets or pipes of the required grade, such as the 300 series. In this process, a large stainless steel part undergoes high-temperature heat treatment followed by water quenching. The part is first heated to 2000 degrees Fahrenheit in a high-temperature furnace, ensuring uniform heating throughout its structure. A flexible thermocouple is attached directly to the part, enabling precise monitoring of the temperature during heating and quenching. Once removed from the furnace, the part is quickly immersed in a quenching tank filled with water to rapidly cool it down. This rapid cooling alters the microstructure of the steel, improving hardness and strength. The entire thermal history, from heating to quenching, is recorded using a portable chart recorder for quality control.